So I want to first talk about so-called correspondence principle, and then I want to talk about lasers a little bit. Okay, let me give you the main idea and then see how Niels Bohr built his model on this idea. So the main idea is, for example, your question, right? Again, at large energies, which means because in the Bohr model we have quantum numbers and energies are parameterized with quantum numbers. Large energies means large quantum numbers. We can think about n much larger than 1 specifically. So we expect quantum mechanics to produce classical mechanics. Okay, so that's like a very powerful statement, and it also says quantum mechanics is like more fundamental than classical mechanics. Classical mechanics emerges from quantum mechanics. So if you know quantum mechanics, you should be able to produce classical mechanics, but not the other way around. But here you'll see Bohr was like very intelligent to produce quantum mechanics from classical mechanics. So I need to like remind you, so from classical electrodynamics, electricity and magnetism. So we know two things. First, electron in the orbit should radiate, right? And we discussed this at length because a circular orbit is a motion with acceleration, and a charge with an acceleration is supposed to radiate radiation. That's the result from electricity and magnetism. But there is one more result. So we have to ask, what is the frequency of expected radiation? Why frequency? Because you know from the Bohr formula we are talking about frequency to parameterize the energy. So it's reasonable to first understand the frequency of expected radiation. So the question is, what is the frequency of radiation? So classically I expect radiation to come out, right? If people ask you like, you are a classical physicist, what do you expect? You answer, you expect radiation. The second question, what is the frequency of radiation? You should also be able to answer that. And there's only one scale in this problem. What could that be? What is the frequency? So you, in like a circular orbit, there's only one parameter, right? There's only one scale. Anybody want to guess?
So
yes.
It's the frequency of electron around the orbit.
Exactly, right? There's nothing else. There's only one frequency, and it's the orbit frequency. And a reasonable person would say, okay, the frequency of this orbit should equal to frequency of radiation if the radiation comes out. Okay, the frequency of radiation should be equal to frequency of electron motion. Because the source is electron motion, the frequencies should match. Now the goal is, okay, the goal then relate electrons energy to frequency. So let's do that. I think last time we derived the total energy. Total energy is half the Coulomb energy. So E is equal to minus a half E squared over, maybe I can, let me write it and next time I use like a shorter notation, so it's something like that. Let me shorten this with minus a half alpha over r, where alpha is equal to e squared over 4 pi epsilon naught. I just don't want to keep writing this thing. So let me use this result we used last time. So let me F Coulomb was equal to F central. Then alpha over r squared should be equal to m v squared over r. Now I want to use this and get an expression for angular momentum, which you will see will be related to frequency. So let me multiply it with m and multiply this with r squared. So cancel this one with this, cancel that one with that. And this thing mvr is angular momentum, so I'm going to call this L squared. Then 1 over r is going to be equal to alpha m divided by L squared. And similarly, E is equal to this, this expression, right? For 1 over r, I can write this expression. So this is going to be minus 1/2 alpha squared m divided by L squared. Is that clear? So I wrote energy in terms of L now, using this 1 over r expression. Now let's calculate change in energy with change in angular momentum. And this is like a simple derivative, right? So this 2 is going to come to front, minus will cancel, and you are going to have alpha squared m divided by L cube. And here I want to show you a factor using the frequency. Frequency is what? Frequency is v over r, right? Or v, the orbital velocity, is radius times the frequency, or the other way around. And for this, I want to use v, okay, this expression, alpha m divided by L squared. And okay, this is for v, this is for 1 over r. And I think I want to divide and multiply with r.
So don't you want to cancel v?
Yes, yes.
So v will be square root of alpha minus mr.
V will be square root of.
From the
I think I see. I think I'm trying to get v times r is going to be angular momentum, right? So this part m. Okay, now I got it. So this part, maybe I can use a color. So this part, m v is p times r is, this is L. And for 1 over r, let's also write alpha m divided by L squared. So I'll cancel this L with this, and at the end, omega will be what? Alpha squared m divided by L cube. Right? There's like L squared here, and there's L here, and in total L cube. Alpha square m L cube. Good. Then, So you can see this side is what? This is omega. Then I can write dE is equal to omega times dL. Good. I think we could write this from the beginning without any derivation, right? For example, in the case of like a kinetic energy momentum, we have dE is equal to velocity times dP, right? We could write exactly the same thing for angular motion, but now we derive this from the Coulomb potential and motion in central field. So this here, this E is frequency of the orbital motion. Let's make this more specific by writing electron. And now let's use the correspondence principle as Bohr used. So correspondence principle. So for large energies, which means for large orbits, there will be a radiation. This is the fact number one. And fact number two, the radiation frequency will be the electron frequency, right? For large orbits, there will be like some h nu photon, right? We are using this from Planck. But this is equal to what? This is h bar, right? I divide and multiply by 2 pi, and this is omega photon. So this is from the photon radiation. And this energy should come from somewhere, and it should come from exactly here, right? The orbital motion changes by dE, and this change should go to the photon. So this one is going to be omega electron times dL. Is that clear? Now use classical electricity and magnetism to call omega photon to be equal to omega electron, right? So I will cancel that with this. From here I reach, let me use from this infinitesimal to finite difference notation, delta L should be equal to h bar. So this means angular momentum changes in quantized way by Planck's constant divided by 2 pi. So if angular momentum increase or decrease by h bar, so we can now conclude what L is. What is L supposed to be if it increase or decrease in h bar? Right? N times h bar. And this is Bohr's quantization. Where n is equal to 1, 2, ... Any questions or comments? Once you obtained the angular momentum quantization, you can reproduce all the results we produced by using de Broglie. Now the key is we produced quantized atom without de Broglie relation. And that was the case because Bohr did his work 10 years prior to de Broglie.
So, and number n what?
N is quantum number, right? N is 1, 2, 3, up to infinity. 3, dot, dot, dot.
Okay, I thought orbits.
Like in the de Broglie case, what we said was like, okay, here is the orbit, and inside this orbit we are feeling like a wave, right? And we were saying that 2 pi r was equal to n times lambda. This is exactly the same n, right? This n quantum number is exactly the same n, but the way we approach the same conclusion is completely different. Any questions or comments? Okay, so why is this important? This is important for the reasons I outlined, and also Einstein recognized that. I think I like this quote and I want to tell this every time. So Einstein, I think Bohr had like one paper with like several results, and he was like calling this the highest form of musicality in the sphere of thought. This is kind of like a famous quote. If you didn't know, he's referring to this result Bohr derived. Good. Any questions or comments? So maybe there are two things I want to mention. One is, maybe I can briefly tell you what it is, and I ask you to read the lecture notes. So indirect evidence for Bohr model, we last time considered it comes from spectra. And spectra was known about like 50, maybe 100 years prior to quantum mechanics. But there was also, once Bohr came up with this model, there was also a direct evidence. And it was so-called Frank-Hertz experiment. So I think this Hertz is, I think, some relative of the other Hertz, maybe his cousin or something, but it's in the family, as is usually the case. Also, I think Bohr was working with both J.J. Thomson and the Rutherford, right? It's not an accident that the person who does the next big thing, comes from the previous big things. So apple doesn't fall far from the tree. And Bohr also gave rise to many influential physicists who also made more remarkable things, which we'll come to in a little bit. So in the Frank-Hertz experiment, so what you do in the Frank-Hertz experiment is something like this. You have these batteries, and they are connected to like a wire like this. And if you give high enough voltage, right, you just start shooting electrons. And what you do is you collect these electrons on the other end, and you measure the voltage. It's kind of like photoelectric effect, but in a different arrangement. And there's also like a meter to see the current. So what you also do is like you put this entire thing in a vacuum like this, and you put inside mercury vapor, right? Okay, this is V. There are some technicalities, like you also put like some what I call is like a, so this one is accelerating potential. I also have like a kind of like a filter to filter out like small noise, but it's not important, so let me not mention it. So what you do in this experiment is like, as V is increased, So this potential just breaks up the electrons and you speed up the electrons. Basically, you give the kinetic energy to electrons and they collide with these mercury atoms, right? So as we increased, electrons collide with mercury with higher kinetic energy. And if they transfer all of their energy to mercury atom, they cannot go to the, they cannot complete the circuit, right? Because they are just like, they lost their kinetic energy, they left somewhere in between, and you are not going to see the resulting current. Whereas if they collide with the mercury and then they just don't lose their kinetic energy, they are going to reach the positive anode and they are going to give rise to a current. But how do we decide if they are going to give their kinetic energy or not? We decide based on the mercury's atomic levels. So if kinetic energy of electrons match level spacing of mercury, so they are going to lose their energy. So electrons lose kinetic energy. As a result, no current, or current will decrease. Now we can think about what's going to happen. So here is our experiment. So here is the result. So this is the current you see in this ammeter, right? And so this is the amount of V you give. If the energy like initially is small, right? Like there is mercury, there is like something like 13.6. If it was hydrogen, it was 13.6. If it's mercury, it's order of 13.6. Not exactly, but not important. Until you reach, so electrons will collide with mercury atoms, but they are not going to excite them. So they are not going to lose their kinetic energy, and they are going to give rise to currents. At some point, whenever you reach the first excited state energy level of the mercury, there will be a reduction in current, right? And as you increase velocities, you are going to go up again, right? And as you increase and increase, so those electrons which couldn't reach the anodes and which were stopped due to losing their kinetic energy will start getting more and more energy from this potential, and at some point there will be another one, right? And at some point there will be another one, and so on. So this is, and now you can do the two things. First, so in mercury, E times V, which is the kinetic energy of electrons, should be equal to this, let me call this minus E1 prime, because it's not exactly 13.6, because it's like different nucleus, and there are also other like complicated effects like screening and all those things, which we'll talk about, but it is going to be 1 over n1 square minus 1 over n2 squared, and we don't care about this, like this is something like 4.6 EV, right? And exactly if you look at here, this is going to be 4.9 EV. So what is more is also like once the mercury atom, like here is like a mercury atom, right? It absorbed energy from electron and its electron went up to a higher level, but that electron is not going to like being there. Eventually it has to go down because there's like a available smaller energy state, right? Why would it stay there? So it is going to come down and there will be radiation out. And you can also look at this radiation and measure its like spectroscopic signature, right? Frank-Hertz also did that, and they found radiation wavelength found at 256.6 nanometers. And now this is like the photon, right? If I do the following, h nu is the photon energy, which is h c over wavelength. How do I know that? I know that because c is equal to lambda times nu, right? And nu is equal to c over lambda. And h is a fundamental constant, c is a fundamental constant, right? And nu is, lambda is given to be this, 256.6 nanometers. If I calculate this number, what do you think I'm going to find? Something on the page? 4.9, right? This is 4.9 eV. So which proves that this is actually the quantization of atomic levels that gives the dip in the current and also the wavelength in the spectrum. Any questions? Maybe in the remaining 5 or 10 minutes, I quickly tell you about lasers, and I will tell you more about lasers in the future. But let me start with like a very quick 5-minute introduction. So the laser means light amplification through stimulated emission of radiation. So this is L. Let me see if I missed LA. Okay, there is no T. This is S. This is E, and this is laser. Okay. So first, now we know the radiation. There are like actually 3 different kinds of radiation. One is ordinary light. Ordinary light. So this is all wavelengths. And it's kind of like a white noise. So what this means is like you have like a wavelength, you have like a smaller wavelength, you have maybe a gigantic wavelength, maybe a very small wavelength. All of them are added up in like this ordinary white light. So we can have monochromatic light. Let me call this monochromatic light. Let's start with out of phase. And what this means is like I have like some light. It's like one photon, and there's like a second photon. But this second photon is, if it was like this, they would be in phase. But if it's just a little bit off the phase, something like that, there'll be another photon, maybe something like that. Maybe another photon, something like that. So this is like a single light, monochromatic, but they are not in phase, right? They are out of phase. So they are out of phase. And lastly, laser. Let me call this laser. A monochromatic light, which is in phase, is like this, but all the photons are exactly synchronized like this. So if you want, you have like a gigantic macroscopic phase, macroscopic wave that's like all in phase. They are all synchronous with each other. And the question is, how can you produce something like that? And for this, we need to think about atomic transitions. And there are basically 3 types. So we are now familiar with atomic transitions, so let's think about a little bit more detail. The first one is stimulated absorption. Stimulated absorption. So in that case, you have, let's say, many levels, but let's focus on 2. One is ground state, one is excited state, and you have like an electron sitting in the ground state, and radiation comes in, and it matches exactly this energy difference. So this is h nu. So h nu is equal to E1 minus E naught. If this exactly happens, you go from here to here. So this is stimulated absorption. Basically, atom absorbs light by increasing its energy. The second one is spontaneous emission. So now in that case, okay, let me go to next line. You have this E1 initially, and the atom is not going to like staying there because there's like a smaller available state. Nobody wants to be in the higher state. And you just basically go down here at the expense of giving a radiation. And this radiation, h nu, is going to match, okay, this is E naught, exactly like before, E1 minus E naught. This is the you spontaneously emit a photon. And third, there's like a third possibility people didn't initially think about. And someone famous pointed that out. Does anybody know? So this is, let me call the name, and maybe you can think about who might have came up with this idea. So this is called stimulated emission, right? So you send light, you both stimulate and you both emit. So you do, you send light, you do both of these 1 and 2 at the same time in a weird way, right? But maybe I give you the picture and you can see. So initially, you have this atom. So this is E1, this is E naught, and you send radiation, and so this gives rise to the same levels. So this guy goes to here. Right? Normally it absorbs this light if it is in the ground state, but it absorbs this light by going to ground state, but there is like an energy difference, and what's going to happen is that it's going to give rise to 2 photons. So this is h nu, so this is h nu. So you basically duplicated the photon you sent, right? You can amplify it. So you have like a photon you want to amplify, you send it to here, and then it like doubles. And this thing is going to be exactly in phase with what you sent. And that's the key idea about the lasers. Any questions or comments? There is a little bit technicality here, but maybe, okay, so this, let me just give you the hint, and then you can go and read lecture notes or your book. So this is key for lasers. So it turns out probability of process 2 is equal to probability for process 3. So basically, stimulated emission is as likely as spontaneous emission. So if you start in this state, you are as likely to give rise to this process as this process, and we'll come to that. So we will see this later. But to achieve that, there's a little bit technicality. So you need so-called meta-stable states that you can put your atoms into, and then when you send the light, these metastable states can produce laser. So states to produce laser, and you can also there are like, maybe you can read 3-level lasers as opposed to 2-level, which I showed you here. 2-level is, for some technical reason, is not possible. You have at least 3-level, or there's also like 4-level lasers. If you are curious, just sit down and read. It's just a 2-page text, and many of you will end up working on lasers, so it may be useful for you later. Okay, any questions? Any comments? So there will be a quiz in the second hour. Today I'm done. Next time I'll continue with Schrödinger equation and more formal quantum mechanics.